Okay, guys. These notes for sections 2 and 3 are going to be broken down into 2 videos, not necessarily section 2 and 3 videos. This one is going to be just giving you the content and the definitions behind electron configurations, and then I'll do another one that's actually showing you how to do the electron configuration so that you're not all having to try to do it all in one sitting. But for the content, you do need to know that Louis de Broglie is a French scientist that suggested that electrons be considered waves and that they were actually confined to a space around the nucleus, not just floating randomly around like was once suggested when with the idea of an electron cloud. Okay, so they had fixed spaces that they could exist in. All right. According to this relationship, which we did in the last notes, that energy is Planck's constant times frequency. These frequencies corresponded to energies. So if you had the frequency, you could then calculate these electrons' energies as well. And those were the quantized energies of those Bohr orbits that you've seen. Okay, so electrons, just like light waves, I know you've probably talked about waves, light waves, and how they can be bent or diffracted. Electrons also can. You're going to need the definition for diffraction and interference in your notes because they're not vocabulary words. So diffraction is the bending of a wave, and then interference occurs when they overlap. Okay. Okay. Heisenberg was a German physicist, and he came up with the Heisenberg uncertainty principle. He said that any attempt to locate an electron would knock it off its course, and then it wouldn't be located there anymore. So he said it was impossible to determine both the position and the velocity at one time. Okay. And then we've all heard about Schrodinger now. Erwin Schrodinger, he developed that equation, and an equation that treated electrons as waves. So here we are, everyone's moving to this idea that we can treat these electrons like waves, all right? So with the Schrodinger wave equation and that Heisenberg uncertainty principle about locating electron, these two basically laid the foundation for all the quantum theory. And remember, quantum theory was one of your vocab words, but just you do need to know that it describes mathematically the wave properties of electrons and other small particles. Okay, so again, I've already said this once, but electrons don't travel in these perfect orbits like Bohr thought. They also don't just float around in a random cloud. They exist in these regions called orbitals, so they can't pinpoint them on a certain path, but they can put them in a region around the nucleus. Okay, so an orbital is a three-dimensional region around the nucleus that indicates a probable location of an electron. Okay, we're going to have 4 orbitals, and I'll get into those when I show you how to do electron configurations, but they are orbital S, P, D, and F. You'll have an opportunity to write those later, but just already wanted to introduce you to them though. All right.
It is very difficult to predict the position of any given electron at any given time. There are, however, regions inside the atom where electrons are likely to be, and other regions where electrons are unlikely to be.
Okay. So more of your vocab word, except in a minute, I'm going to explain to you, hopefully more clear, exactly what these quantum numbers are. It's basically different properties of these electrons as we're doing configurations and what they stand for. So hopefully you'll have a better idea of especially principal, quantum, and angular momentum in just a minute whenever I actually tell you what those mean and show you what they mean on configurations. Okay, like I said, more vocab words. I hope to explain these better as I'm showing you those configurations.
The principal quantum number n is a positive integer describing the energy level of the electron. For example, an electron for which n equals 1 occupies the first or lowest main energy level and is located closest to the nucleus. The angular momentum quantum number L can be any integer from 0 to n minus 1 and describes the shape of the orbital.
These are those orbitals.
The s orbital can be represented by a sphere. The p orbital can be represented by a dumbbell shape. The d orbital is primarily shaped like cross dumbbells, but can also have a fifth dumbbell ring shape. The magnetic quantum number m can be any integer from -1 to +1 and describes the orientation of the orbital. Orbitals run along the x-axis, the y-axis, and the z-axis, as shown in this p orbital. The spin quantum number has only two possible values, +1/2 and -1/2, which indicate the two fundamental spin states of an electron in an orbital. A single orbital can hold a maximum of 2 electrons, which must have opposite spins.
Okay, you will not be responsible for knowing any of the d orbitals, okay? The only ones that you will be responsible for knowing is s's, which they're all spheres, okay? The only difference is they just get bigger. So if this is a 1s, then the 2s would be a little bit bigger around. The 3s would be bigger than that. So those are the s's. They're very simple. They're just spheres. The p orbitals are just dumbbells. They're all shaped like a dumbbell. The only thing is that they lay on these different axes. So you've got the up and down, which is the z. You've got the across, which is the x, and then the y is kind of an angle through the two. Okay, so those are the three ways that those dumbbells can lay. But like the s's, as you go up, like if this is a 1, if this is a 2p, okay, and you went up to 3p, it would just be a bigger dumbbell, okay? So there are 3 orientations for p, only one for s. But know that s's are spheres and p's are dumbbell shaped, and there are 3 possible orientations for p. Don't worry about d. We're not going to get into d. Okay, I'm going to get into showing you these electron configurations in just a minute, but as I'm showing to you, we will be drawing boxes to represent orbitals, and these arrows represent electrons, okay?
Electron configuration can be indicated by orbital notation. In orbital notation, an unoccupied orbital is represented by a line. The lines are labeled with the principal quantum number and sublevel letter. An orbital containing 1 electron is represented by a line with 1 arrow pointing up.
Okay, we don't do ours just like this, so it's similar, but I'll show you in a minute. So I don't want to go through that video because we do ours just a little different. So I don't want to go through the whole thing. Okay, don't need any of that. Sorry, I know I clicked through it quick because you really don't need it. Did we miss off ball? Okay, sorry, I'm clicking through quickly because you don't need any of this. If you did, I would let you know. Good, I'm just making sure. Okay, all right, so in the next video, I will show you how to do the electron configurations.